So in this lecture we will study about carbocations, and in this list, first of all we will study about structure of carbocations, and then methods of generation of carbocations, and then we will talk about stability of carbocations, then reactivity, and then some reactions related to carbocation. Structure. So how carbocation look like? Let's see a simple case. So this is a carbocation. You can see that this is vacant orbital, and here it will be without any electron. So this is positively charged, and angle between substituent bonds is 120 degree. So this is structure of carbocation. You can see that central carbon atom is trivalent, and this carbon atom is holding set of electrons, because 2, 4, 2, 6, and the vacant orbital has positive charge because it has no electron present in it. So this is structure of carbocation. The next topic is generation of carbocation. So carbocations can be generated with different methods. First method, ionization. So how this method works, let us see. So what happens that suppose we have alkyl halide. So we want to make carbocation out of it. How we do it? You see that electrons from this bond will go to halide, and this remaining R becomes positively charged, or you can say carbocation. Okay. So this method is called ionization. In this ionization method, what we do is we have alkyl halide, and when we ionize this, the electrons from this bond goes to halide group, and R becomes positively charged, hence it is carbocation. This is simpler method. The next method to generate carbocation is ionization after initial reaction. Suppose we have a functional group in a organic compound, and that functional group ionization occurs in an initial stage. For example, we have alcohol group. So if there is proton present in that proton, so proton will react to this oxygen, making a oxonium ion, and in next step you will get a carbocation plus H2O, because these electrons will go to oxonium ion to form water, and we are left with carbocation. So these are the two methods through which we can generate carbocation. Third method of generating carbocation is attack of pi system on electrophile. You know what is electrophile? Electrophile is electron loving species, and when pi system attacks on electrophile, we will get a carbocation. Suppose we have an pi system. This is a pi system, and here we have a electrophile. So what happens is this pi system attacks on electrophile. So what we will get that and here we will get positive charge, because if pi electron is donating electron to this proton, this carbon atom will be left with positive charge. So we will get a carbocation. So these are three methods through which we can get carbocations. Now we will talk about stability of carbocations, and in this we will talk about three factors on which stability of carbocations depends on. So first of all is inductive effect. This is inductive effect. So positive inductive effect will lead to more stable carbocations. Positive inductive effect will lead to more stability of carbocations. You know what is positive inductive effect? Positive inductive effect is that you have more alkyl groups, for example, and negative inductive effect leads to less stability of carbocations. In hyperconjugation, if we have a sigma bond in conjugation with a carbon atom having a positive charge, so positive charge can delocalize in that molecule. For example, if we have this molecule, so here you can see that this is a carbocation, this is empty pz orbital, this is p orbital which is empty. So it can hyperconjugate in such a way that this hydrogen can transfer to this empty p orbital and the positive charge goes to this side. In next step, we will find that here becomes positive charge and here we will get hydrogen and alkyl groups which were present earlier. So this is the concept of hyperconjugation. You see that positive charge from this side goes to this side and hydrogen shift from here to here. It means positive charge, when positive charge delocalizes, it provides stability to carbocation. Now, resonance effect. How resonance affects the stability of carbocations. Suppose we have these two molecules. In one molecule we have positive charge adjacent to this oxygen group, and in another molecule we have positive charge in this position with respect to oxygen atom. So what will happen that this molecule will be more stable than this molecule. Why? Because of the resonance effect. Because in this particular molecule, this positive charge can be shifted here, because if this lone pair of oxygen can provide electrons to form a double bond here, I will show how. You see that these electrons of oxygen goes to form a double bond here and provide a positive charge here, and this positive charge is no more here. So there is shifting of positive charge due to resonance effect. This is resonance. So this molecule is more stable than this, because here it has no resonance effect in it. Now we will see about reactivity of carbocation. How carbocations react. Suppose we have a carbocation here and we have a nucleophile here. So they will react as alright, because this is nucleophile. This will attack on these carbocations to form a bond. Simple. In next case, we have a carbocation. We have this carbocation. So there can be a 1,2 hydrogen shift. There can be a 1,2 hydrogen shift to form you can see the positive charge is shifted to this side, and this is 1,2 hydrogen shift. You see that positive charge is shifted from this side to this side and forming a carbocation here, and as you can see here the carbocation was primary. Here the carbocation was primary, and in the product the carbocation is tertiary, because this is alkyl group, this is alkyl group, and this is alkyl group. So this is our tertiary carbocation. So you saw how primary carbocation can be converted to tertiary carbocation by 1,2 hydrogen shift. So the arrow from this side to this side. So these were the 3 cases involving reactivity of carbocations. Now we'll see a couple of reactions involving carbocations, and first of them is Pinacol-Pinacolone rearrangement. So see, this is Pinacol, and in IUPAC name it can be named as 2,3-dimethyl butane 2,3-diol. Okay, this is Pinacol. In short form, in common name, we can call it Pinacol, and in IPSC naming, it can be named as 2,3-dimethyl butane 2,3-diol. Okay, so if we react this Pinacol with a proton, what happens that this proton can go here, forming a oxonium ion here. And now in next step, what will happen that this oxonium ion will get electrons from here and it will lose water from here, and this methyl group will be shifted to this carbon. See how? As you can see, the methyl group has shifted to this side, and here it remains a positive charge on this carbon and thus becomes a carbocation. And in next step, what will happen that oxygen and hydrogen bond will be broken up, and electrons from those bond will be gone to this bond, and here it will make a double bond, losing a proton. See how? As you can see, by losing a proton, here becomes a double bond, and what we get in the product is a carbonyl group, and this molecule can be named as Pinacol. So Pinacol is named as tertiary butyl methyl ketone, which is named as Pinacol in common language. Our next reaction involving carbocation is Tiffeneau Demjanov reaction. What this reaction is, let's see. We have aminomethyl carbinol in a reactant, and what will happen that when we react this aminomethyl carbinol to nitrous acid, we will get this, and in next step nitrogen will be released, and we will get this carbocation, and in next step this alkyl group will be shifted to this side, as you can see the alkyl group has been shifted to this side and forming a positive charge in this side, and in next step the bond of O and H will be broken, and the electron from those will come to form a double bond here, releasing a H positive. As you can see that the ketone is formed from the aminomethyl carbinol. So yeah, we can get a ketone. This is called Tiffeneau Demjanov reaction. So this was all about carbocations, and in the next lecture we will talk about carboanions.